Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the 11th chapter of microwave engineering, where the microwave resonators we have been addressing so far.
So far in this chapter,
Very
we
first
have
of all,
gone
we
through
have
first of all the
addressed the
understanding
series
of the
and parallel
series
type of
and
the
parallel
resonant
resonant
circuitries,
circuit,
and also
the
address the
loaded
short
and
circuited and
unloaded
open
types of the
circuited
quality
conditions
factors.
with respect to the
Next to that, we
microwave
have also
transmission
gone
lines
through
having the
the
lengths
conditions for
lambda
short
by 2
circuiting
and lambda by
and
4.
open
We have
circuiting when
also
the
addressed with
microwave
respect to the
transmission lines
loading
are
and
related to the
unloading
length
of the quality factor
corresponding to lambda
and
by 2
introduced that
and lambda
Q
by 4
factor there.
there.
Next to
Now,
that, we have
while we have
converted
the
the
modifications
waveguides
from the
into the cavity
waveguides to that
resonators
of
by
the
closing
cavity
the two
resonator,
walls
we
with the
have
help of
closed both the
shortening plates.
walls.
Hence,
Those
we
were
have the
open
rectangular,
for the rectangular
circular,
and circular
and the
waveguides with the
semicircular
shorting
cavity
plates. And
resonators.
now
We have
we have
also
the
practiced
rectangular
few of
and
the
circular
selected
cavity
problems based on to
resonators.
this cavity
If the cross
resonators.
section is
So
not
now,
either
in this particular
rectangular,
topic,
not
we shall
complete
be
circular,
addressing here
but a semicircular,
the
so that
quality
time
with
we
respect
shall be
to
having the
these
device called
cavity
as
resonators
semicircular
especially. So
cavity
let us see the
resonator.
details.
So
So here we start with our topic, quality factor of a cavity resonator. So in general, the quality factor, as before, I hope it is very clear that it is simply represented by capital Q. And for the cavity resonator, it is the measure of frequency selectivity at the resonant and anti-resonant circuits, I can say here. So how it is represented with the frequency selectivity? So for that purpose, we simply provide the definition of quality factor in the form of a ratio. That ratio is of 2 pi times we have the numerator given by the maximum energy stored, whereas the denominator is energy dissipated per cycle. So as the energy is dissipated per cycle, so it has a periodic nature here. So the periodicity refers to that of the frequency. Hence, we can say that the quality factor is having the frequency selectivity. So further, the quality factor capital Q can be expressed as we have 2 pi in multiplication to the ratio of maximum values of energy stored and that of the dissipated here, we represent 2 pi into the frequency, that it is angular frequency, by simply omega in multiplication to capital W divided by capital P here. So this is very important formula providing the basic definition to the quality factor for a cavity resonator here. So in this expression, the simple representation, capital W is equal to maximum energy stored, whereas capital P we have here to be the average power loss, we can say. So this is the simple definition we can make corresponding to the quality factor of cavity resonator. Now what happens at the resonant frequency? At the resonant frequencies, the resonant frequency that has been represented by F suffix R, we have the electric energy, let us say we can represent it as W suffix E, and that of the magnetic energy W suffix M are equal and in time quadrature. So time quadrature means that when the electric energy is maximum, so that time the magnetic energy is equal to 0, and when the magnetic energy is at maximum, the electric energy is equal to 0. So this is a vice versa relationship with respect to the energy storage of electric and that of the magnetic components, we can say that. Now the total energy stored into the resonator can be obtained by having a simple integration with respect to the energy density over the volume of the resonator. So therefore we can express the total energy stored W suffix E is equal to the volume integral V in multiplication 2 over it, we have epsilon divided by 2 into mod of capital E, which is squared into dV. So this can be equal to W suffix M also, which can further be expressed as the volume integral mu suffix 2 into mod of H square into dV here, which is equal to capital W. So W suffix E we relate with the help of epsilon, that is the permittivity, how much permissible a certain dielectric material is there to the flow of electricity through it. Hence we have taken it for the electrical component here. Whereas if we have the use of H, magnetic field intensity vector, instead of electric field intensity vector, and epsilon, so in place of epsilon we have mu, permeability of the medium, how much permissible a given material is there to the flow of magnetism through it, that it is mu. So that time we can represent it by W suffix M, the magnetic component. So both are nothing but the same, giving us the energy content in general represented by capital W. So in the previous expressions, whatever the capital E in terms of mod and capital H in the representation as a mod is there, these are nothing but the peak values for the corresponding electric and magnetic field vectors, and at the resonance condition these peak values are same. Now as the definition of quality factor we have seen, capital Q is equal to omega into W divided by P here. So W we have just now discussed, so that it is the energy stored. The energy dissipated per cycle, that is nothing but the power, the denominator is to be discussed now. So therefore here we have the average power loss, as it is dissipation of the energy per cycle, we can say it is average power loss, that can be represented by capital P here, and it is evaluated by again having the integration, but here the integration is surface integral over the power density. So the power density over the interior surface of the resonator walls we can say here. So this is expressed as capital R suffix S, the surface resistance of the metallic walls, divided by 2 into the integral over surface, that it is double integral for mod of HT squared into dA. So here dA refers to the differential area of the surface, whereas HT in the mod is the peak amplitude of the tangential component here. So T is for mentioning the tangential, whereas RS is the surface resistance of the walls of the resonator body there. Now if we can have the expression of power loss, this one, and the expression of the energy, the previous one, substituted into the first equation of the Q here, we have the quality factor in general capital Q obtained as omega mu into volume integral mod of H square into dV divided by RS surface integral mod of HT square into dA. So this will be the expression for quality factor in general. Now as we can resolve a certain vector in terms of its normal component and tangential component, we can express it for magnetic field intensity vector. So in this regard we can have mod H square. So we have a square of mod H, so this is equal to square of mod HT, the tangential component, plus the square of mod HN, the normal component. So if it applies to the peak value for the normal and the tangential component, the another representation of the quality factor Q can be given as omega into mu into the volume after the integral divided by twice into Rs into the surface area after the integration here. So this can be the another general formalization for the quality factor concerning the cavity resonator. Now in the start of this chapter we have addressed the unloaded and the loaded type of the quality factor corresponding to the resonant circuitries for the series parallel with the help of the lumped elements here. Now for the cavity resonant circuitries here we can also have this one. So the unloaded condition, if you talk about, we generally represent the quality factor by q suffix 0, whereas the loaded condition is represented by q suffix l here. So for the unloaded resonator, the representation with the help of either series or a parallel circuitry that we have reported is there, and the corresponding resonant frequency is simply represented as f suffix 0, whereas for the loaded case the general representation f suffix r with the suffix l can also be referred to as. So for unloaded we simply have the angular frequency omega suffix 0 into capital L divided by capital R, because whatever the energy storage we have, that can be accounted in this particular inductance, whereas the dissipation of the energy is of pure resistive form, hence we have represented capital R to the denominator here. Whereas the resonant frequency for the unloaded condition, we can give it by a simple formulation 1 upon 2 pi under root of capital LC here. So I just mention here, this is the unloaded condition, whereas these are the representation for loaded condition. Now let us explore the loaded condition into the more details. If we imagine that the cavity is coupled by means of ideal type of the transformer and a series inductance, so that time the cavity coupling circuitry can be shown as, here we have the generator. So the generator supply is V suffix G. It has the internal impedance represented as Z suffix G, and it is connected in series to that of the inductor here. So let us say it is L suffix S for series connection, and now here it is the transformer for the coupling purpose. This is the another turning on the another hand of transformer, and now this transformer will be connected at the another end to the load, we can say. Those will be having resistive component, the inductive component, and the capacitive component. So in general we represent it as capital R, capital L, and capital C. So this is the transformer. At ideal condition we can get it to n:1 type of the coupling here. So the equivalent circuitry of the same can be drawn in this fashion, where we have the generator shown, and as we have n:1 type of coupling with the help of transformer, we can denote it as capital N times Vg here, whereas its internal impedance that we have represented here is also capital N square into Z suffix G, that has been modified. In series here we have the inductor component here, so this is equal to also N square times Ls here. Now here it is the node, this is also extending to the node here, where we have the connections for resistance, inductor, and the capacitor here. So capacitor is C, inductor is L, and resistor is R here. So this is the equivalent circuitry after coupling. So with respect to such equivalent circuitry, we can express the loaded type of the quality factor represented Q suffix L. It is expressed as the angular frequency omega suffix 0 in multiplication to the inductance L divided by, here we shall be having R added to N square Z suffix G. So this is the representation for the condition where we have mod of N square Ls is very less than that of the mod of R added to N square Z suffix G. So that time we can express this component in the denominator only, as it is very greater than this component here. Now here we have a coupling done. So the corresponding coupling coefficient can be denoted as capital K, and it can be simply defined as N square Z suffix G divided by the pure resistance component capital R. Further, the loaded quality factor QL becomes omega 0 L divided by R in the bracket 1 plus this coupling coefficient K here. So in general, absorbing omega 0 L and R together, we can write it to the form capital Q0, that is of unloaded condition, which is divided by 1 plus capital K here. So the rearrangement of the above equation that has a relationship with the unloaded quality factor and the loaded quality factor, we can express 1 upon Q suffix L, the loaded quality factor, is equal to 1 upon Q0 unloaded quality factor added to 1 upon Q suffix EXT. So this expression, this relation is very important as far as the quality factors for the cavity resonators are concerned, and in this expression the substitution is done in the representation of Q suffix EXT for Q0 divided by K, which is omega 0 L divided by K into R here. So EXT refers to the external quality factor. External quality factor. So in this equation we have the three types of the quality factors: unloaded quality factor, loaded quality factor, and external quality factor. So as we have defined a coupling coefficient capital K, depending on the various situations, we can have the three types of the coupling here. The first one is called as critical coupling here. In the critical coupling, we have the coupling coefficient K is equal to 1. So we obtain K is equal to 1 when the resonator is perfectly matched to that of the generator, as can be seen in the equivalent circuitry diagram. So when we have K is equal to 1, we have just talked about it to be the critical condition of the coupling here. The loaded quality factor Q suffix L can be expressed as half of Q suffix EXT, the external quality factor, and it is also half of Q suffix 0, that it is half of the, we have unloaded quality factor here it is. Now next to that, if we have the coupling coefficient capital K to be greater than 1, so that time we can say this is overcoupling. So the overcoupling is designated by coupling coefficient K greater than 1, and in that situation capital K can achieve the value of rho. The rho is the representation of the standing wave ratio. So thereupon inside the cavity resonator we expect the formation of the standing wave there. So here when we have K is equal to rho for overcoupling here, so that time the loaded quality factor QL is expressed as Q0 divided by 1 plus rho here. So the loaded quality factor is equal to unloaded quality factor divided by 1 plus standing wave ratio value. Now the last situation is to be addressed corresponding to the value of coupling coefficient K here. So when the coupling coefficient K is less than that of the 1, we have talked about the condition K is equal to 1, that is critical type of the coupling here. When K is greater than 1, it is over type of coupling, over coupling we say here. So K less than 1 is called as under coupling. So the condition of under coupling is designated by K less than 1, and at this time we obtain K is equal to 1 divided by standing wave ratio rho. So as in the overcoupling, rho itself was to be equal to coupling coefficient K, getting its inverse will be giving us the lowest possible value, and this leads to the loaded quality factor QL in the form rho divided by rho plus 1 in multiplication to the unloaded quality factor Q0 here. So this is also the important relation to determine the loaded quality factor value when we are known to the value of unloading condition and the value of standing wave ratio corresponding to the formation of standing wave due to the reflections from the walls of the cavity resonator. Now let us discuss about a relationship between the coupling coefficient K and that of the standing wave ratio, that it is rho here. So here we have a plot corresponding to the graphical axis. So on the horizontal axis we take the representation of capital K. This is nothing but the coupling coefficient. Now for coupling coefficient we start at 0 and we have the values 1, 2, 3, 4 and so on in this particular direction. Whereas onto the vertical axis we take rho, which is called as standing wave ratio. And for the standing wave ratio, when we start at 0, we go with the values 1, 2, 3, 4, 5, 6, 7 and so on. So as the three situations we know corresponding to the value of K here, at K is equal to 1, we come to see the critical type of the coupling here. So here we can make a marking from rho is equal to 1 and K is equal to 1. So this is the point that is of critical type of coupling here. When K is greater than this one, so that time the relationship between the standing wave ratio rho and that of K is having a linear relationship, and with the increase into the K, the standing wave ratio is also increasing here. So we have such a graph here. So I say here this is over coupled graph here. So this is the over coupled nature we have obtained in between rho versus K. Now when we have K less than that of the 1 here, so in that particular situation we have a negative drop right from this value, so up to the point where we have the critical type of the coupling here. So here we can say this is the undercoupled situation with respect to the relationship between the standing wave ratio rho and that of the capital K here. So this was all about the quality factor corresponding to the cavity resonator here. By the next lecture we shall be having a practice of two simple problems in the next two subsequent lectures here, continuing into the same chapter, microwave resonator. So I hope you enjoy learning for the microwave engineering topics. For more information and the details, you can subscribe to Ekeeda channel. Thank you.